So we've got 3 bags, A, B and C, each containing 1 red marble and some green marbles. And we know that bag A contains 1 red marble and 9 green marbles only. Bag B contains 1 red marble and 4 green marbles only. And bag C contains 1 red marble and 2 green marbles only. Sasha selects at random 1 marble from bag A. If he selects a red marble, he stops selecting. If the marble is green, he continues by selecting at random 1 marble from bag B. If he selects a red marble, again, he stops selecting. If the marble is green, he continues by selecting random 1 marble from bag C. And part A says we need to get all this information and represent it in a tree diagram. And this is for 2 marks. So I'm going to go back up and look at the information again. And we can see, so in bag A, B and C, we've got 1 red marble and a different number of green marbles. So I'm just going to work out how many marbles there are in total. So in bag A, there's going to be 1 plus 9. So that's 10. In bag B, it's going to be 1 plus 4. So 5. And in bag C, 1 plus 2. So it equals 3. Now we need to create a tree diagram. Now we know there are 2 possibilities because he could either choose a red marble or a green marble. So we're going to have 2 branches coming off at the start. And it could either be green or red. So we're starting with bag A. So it contains 1 red marble and 9 green marbles. So there are 10 in total. So there's a 1 in 10 chance of choosing a red marble or a 9 in 10 chance of choosing a green marble. Then we're going to move on to the next one. It says if he selects a red marble, he stops selecting. So if he goes down this path and chooses a red one, well, he stops selecting, there's nothing else. So we don't need to have any branches coming off of here. Instead, we're going to then have 2 branches coming off of green. Because if the marble is green, he continues selecting at random 1 marble from bag B. Well, bag B has 1 red marble and 4 green marbles. And there are 5 in total. So for it being red, there's a 1 in 5 chance of choosing red. And there are 4 green marbles, there's a 4 in 5 chance of choosing green. And look at the next part. Again, it says if he selects a red marble, he stops selecting, so that's the end of that branch. However, if the marble is green, he continues selecting 1 from bag C. So again, there's 2 possibilities in bag C. We've got green or red. And there's 1 red one and 3 in total, so it's a third for red. And 2 green marbles, so it's 2 out of 3 for green. And that is our completed tree diagram for part A. And for getting that all correct, we will get 2 marks. So part B says we need to find the probability that Sasha selects 3 green marbles for 2 marks. Okay, so if he selects 3 green marbles, then he's going to be choosing this path. So it's going to be here, here, and here. And what I've written down here, as I said, for and, we need to use multiplication. So essentially what we're doing is he's choosing this path, and this path, and this path. So what we need to do is multiply them all together. So probability of 3 green marbles equals, and then multiplying them all together, we're going to get 9 out of 10. Multiplied by, because it's and, so it's 9 out of 10, and 4 over 5, and 2 over 3, which gives us 12 over 25, which is the final answer. So we get 1 mark here for realising that we need to use multiplication and picking the right numbers from the tree diagram. And then we get a final mark here for the correct probability. Now part C says, find the probability that Sasha selects at least 1 marble of each colour. I'm going to use the tree diagram to help visualise this a little bit. So we know that from the first bag he has to choose green, because if he chooses red, then that's a dead end. He can't then choose a green one. So he has to choose a green one to start with. So we go down here, and then he could choose red, and then we're done. We've chosen 1 of each colour. So we could do this one and this one. And because it's and, we're going to multiply, so it's 9 over 10 multiplied by 1 over 5. However, that's not the only possibility. What could happen is he chooses green, and then red, and that will still satisfy the condition that there's at least 1 marble of each colour. So what we're going to do is add to this, because for or we use addition. So it could be this, or it could be this. So we're going to add, and then we're going to multiply these together because it's and. So 9 out of 10 multiplied by 4 over 5 multiplied by 1 over 3. And if we put that into the calculator, that equals 21 over 50, which is our final answer for part C. So we're going to get 1 mark here for all this. So work out that we have these 2 different possibilities and adding them together. Then we get a final mark for the correct answer, 21 over 50. Now part D says Sasha selects a red marble, and we need to find the probability that he selects it from bag B, and this is for 2 marks. So I've written down here from the formula booklet our conditional probability formula. And in the formula booklet it's using the letters A and B. However, in this case I've used E and F, so we don't get confused with bag A and bag B. However, it means exactly the same thing. Basically, here what it's saying is the probability of E, and this line is essentially a mathematical way of saying given that. So here we've got the probability of E given that F. And this is what we need for this question, because this is a given that question. So writing this out in context, what we want to find is the probability, and we're working with the red marbles, so the probability that from bag B, we're going to select a red, given that a red marble is selected. So labelling it, we've got red from B to be E, and red selected to be F. We can now use the formula from the formula booklet. So we've got the probability of E intersection F, so essentially the common bit between them both. In this case, essentially it's the probability of there being a red from B. The only way to get a red from B would be going down this path and then down this path. So the probability of E intersection F, so the probability of a red from B, in this case would be 9 over 10 multiplied by 1 over 5. So on the top we're going to have 9 over 10 multiplied by 1 over 5. Okay, so now on the bottom we're going to have the probability of F. So in this case the probability of a red being selected. Well, we've got a few different possibilities. We've got 1 over 10, because you go straight down that path. Or, so we're going to add this path here. So 9 over 10 multiplied by 1 over 5. Or 9 over 10 multiplied by 4 over 5 multiplied by 1 over 3. We're going to get, on the top, we're going to get 9 over 50. All over 13 over 25. Which equals 9 over 26. Which is the final probability. So we get 1 mark for all this work up here. And we get the second and final mark for the correct answer here. The partially completed box plot in Figure 1 shows the distribution of daily mean temperatures using data from the large dataset for Beijing in 2015. And down here it says an outlier is defined as a value more than 1.5 times the interquartile range below the first quartile, or more than 1.5 times the interquartile range above the third quartile. The 3 lowest air temperatures in the dataset are 7.6 degrees, 8.1 degrees and 9.1 degrees. The highest air temperature in the dataset is 32.5 degrees. And part A says we need to complete the box plot in Figure 1 showing clearly any outliers. And this is for 4 marks. So look up at Figure 1, we can see we've got a partially completed box plot. And from that I'm going to look and try and extract any data that we need but don't already have. So what I think would be useful to get is the lower quartile and the upper quartile. And we can get that data from Figure 1, because this line here is the upper quartile. If I extend that line down here, we can see that's at 26.6. And we're going to do the same for the lower quartile. So that's going to be at 19.4. Now from that we can work out what the interquartile range is by taking the difference. The interquartile range equals 26.6. Take away 19.4, which equals 7.2. So now using this, we can work out which of these points we've been given here are outliers and which of them aren't outliers, using these conditions set out here. So firstly, I'm going to start with this line here. So more than 1.5 times the interquartile range below the lower quartile. So if I do 1.5 times 7.2, which is the interquartile range, we get that equals 10.8. So then using that here, I'm going to do for the lower quartile, so that's 19.4. Then we're going to subtract from that 10.8 and see what we get. So that's 8.6. So according to this condition here, anything less than 8.6 is an outlier. So we can say therefore, so look at these three here, we've got 7.6 and 8.1 are less than 8.6. We know 7.6 degrees and 8.1 degrees are outliers. Okay, fantastic. Now what we can do actually is mark those on. So it says we need to clearly show any outliers. So I'm going to go across to 7.6. I'm going to go across here to show that we've got an outlier. Here. Then the other outlier is at 8.1. So we worked out that these two are our outliers at the bottom. So we know that 9.1 is the lowest value that the box plot goes to, with it not being an outlier. So we're going to draw our line on there and then attach that to the box. Now we're going to take a look at the upper end of the box plot using this condition here. So we know it's an outlier if it's more than 1.5 times above the upper quartile. So again, we're still using this 10.8 value we worked out. If we do the upper quartile, which is 26.6, and we're going to add 10.8 like it says in the condition, we're going to get 37.4. Okay, so 32.5 here is actually less than 37.4, so therefore it's not an outlier. So we know that 32.5 degrees is our upper value included in the box plot. So drawing a line in there, and then we're going to connect it up to our box. And that's great, we completed part A. We've successfully drawn the completed box plot and clearly showed any outliers. So we get our first mark here for successfully working out the interquartile range. We get our second mark here for working out this 8.6 value, which allows us to deduce which values are outliers and which aren't outliers. And then we get the rest of the marks for actually plotting the box plot. So we get one for doing the upper whisker here at 32.5. We get another one for doing the lower whisker here at 9.1. Then we get the fourth and final mark for getting both of these outliers here. So part B says we need to use our knowledge of the large dataset to suggest from which month the two outliers are likely to have come from, and they're likely to have come from October. And the reason for this, if we look at the large dataset, we see that the data is going from May to October. Now the two outliers we've got in this question are down on the left hand side where the colder temperatures are. And if we think about where Beijing is, so it's in Japan, in the northern hemisphere, and between May and October, so that's going between spring and the autumn. So the time when these outliers, these colder temperatures are most likely to be, not in spring, but in autumn, so in October. So that's when it's more likely to be, so that's why the answer is October. And we get our 1 mark for saying that the month is October. So using the data from the large dataset, Simon produced the following summary statistics for the daily mean air temperature, X degrees for Beijing in 2015. Part C says we need to show that to 3 significant figures the standard deviation is 5.19 degrees, and this is for 1 mark. So in the formula booklet we get this formula for the standard deviation. Essentially what this means is the summation of x minus x bar all squared. So we've got enough information to work with this. So the standard deviation equals the square root. And referring to the formula here, we're going to have this number all over n, which is 184, which equals 26.917967 ... which equals 5.188 ... which then equals the 5.19 we wanted to show to 3 significant figures. And we get a 1 mark for showing how we implemented the formula for standard deviation to get down to 5.19. So Simon decides to model the air temperatures with a random variable. Part D says we need to use Simon's model to calculate the 10th and 90th interceptile range, and this is for 3 marks. We can see here that he's decided to model it with a normal distribution. So now down here I've drawn a little diagram so we can sort of visually represent the normal distribution. Now in a normal distribution, the area under the curve equals 1. If we want to calculate the 10th and 90th interpercentile range, we need to work out the 90th percentile and the 10th percentile. So if we label this one here as a 90th percentile, due to the fact that the area under the curve is 1, this means that the area to the left of the 90th percentile is 0.9. And for the same reason, we know that the area to the left of the 10th percentile is 0.1. So I'm going to write this in a bit of a different way. I'm going to say the probability that t, which is our random variable, is less than the 90th percentile equals 0.9, and the probability that t is less than the 10th percentile is 0.1. And our job now is to work out what the 90th percentile and the 10th percentile is. And to do that, we can use the inverse normal modes on our calculator. But first, we need to work out what mu and sigma are. Because we've been given the details of the distribution up here. We know that this is mu and this is sigma. So writing that clearly down here, we've got that mu is 22.6 and sigma equals 5.19. So I've got some screenshots of what it will look like on your calculator when you go to inverse normal mode. So on the graphical calculator here, we need to make sure we select the left tail. So as we can see here, that's what we're working with. And on the scientific calculator here, it's automatically the left tail, so we don't need to worry about that. And so firstly, for working out the 90th percentile, we put in that the area is 0.9. And then we put our mu and sigma in, as we got told in the model in the question. Then when you press enter, it will give you this value, which is the 90th percentile. So we know that P90 equals 29.251 ... Then work out the 10th percentile, we get that that's 15.948. And we get that by setting the area to be 0.1 on the calculator and leaving the rest of the settings the same. And lastly, to get the interpercentile range, we need to take the difference between these. It's going to have 29.251 minus 15.948, which equals 13.3 to 1 decimal place. And that is our final answer. So we get 1 mark here for working out both of these percentiles. We get a second mark here for taking the difference. And we get a final mark here for getting the correct answer of 13.3. Lastly, we're told that Simon wants to model another variable from the large dataset for Beijing using a normal distribution, and part E says we need to state two variables from the large dataset for Beijing that are not suitable to be modelled by a normal distribution, giving a reason for our answer. And this for 2 marks. And we need to make sure we list two variables, because we might read this quickly and just list one and lose a mark. So make sure we list two. Now we need to have a think about what variables are included in the dataset. So there are a variety of different ones. But think about what can't be modelled by the normal distribution is actually qualitative data or categorical data. And think about the variables. So one that would fit this would be daily mean wind speed. So this is measured in the Beaufort scale, which is a discrete scale of 13 values going from 0 to 12. It's categorical. So in the sense 0 will be calm, all the way up to 12 being a hurricane. So it's different categories. And you couldn't model this on a normal distribution. So this is the first one. Now, think about another variable that couldn't be suited for the normal distribution. And this is actually for a bit of a different reason, but one of the variables is the rainfall. And if we look at the data for Beijing in 2015, between May and October, we can see that actually there are lots of days with 0 rainfall. And there's not really very much rainfall at all during this period. And this leads to the data not being symmetric. And for data to be modelled by a normal distribution, it needs to be symmetric. And because if you imagine the normal distribution, it's sort of a bell-shaped curve. And as the data is not symmetric, because of the overall low rainfall and the high amount of days with 0 rainfall, the data would then be skewed. So it wouldn't create a bell-shaped curve. So it wouldn't be suitable to be modelled by a normal distribution. And to get all the marks of this question, you need to have 2 valid variables and 2 valid reasons. Barbara is investigating the relationship between average income and average annual carbon dioxide emissions for different countries. She takes a random sample of 24 countries and finds the product moment correlation coefficient between the average annual CO2 emissions and average income to be 0.446. Part A says we need to state our hypothesis clearly and test at the 5% significance level whether or not the product moment correlation coefficient for all countries is greater than 0. And this for 3 marks. Firstly, we need to state our hypotheses. So our null hypothesis, so H0, we can say that rho equals 0. Then our alternative hypothesis, so H1, is that rho, and looking back up at the question, we see we're testing whether or not the product moment correlation coefficient is greater than 0. So because it's saying it's greater than 0, our alternative hypothesis is going to be that rho is greater than 0. So the next thing we need to do is find our critical value. So to do that, we're going to use the tables, but we need a bit of information first. So back up at the question, we need the significance level. So it tells us it's at the 5% significance level. We also know it's a sample of 24 countries. So we can say, okay, so n equals 24, so our sample size is 24, and the significance level equals 5%. So what I've got over here is a snippet of the table. So we need to cross-reference it to find our critical value. So going down the sample size column on the right, okay, so we've got a sample size of 24, and the significance level, so it's 5%, so that's 0.05 if we're representing a decimal. So we know that our critical value is 0.3438. So now I'm just going to draw out a little line to help us visualize the next bit. So if we imagine in the middle at 0, it goes down to -1 and goes up to 1. Our critical value is 0.3438. I'm going to label that on really roughly, so somewhere like here. And because we're testing, so we're seeing if it's greater than 0, this area here is our critical region. And the product moment correlation coefficient that Barbara found was 0.446. And okay, that's great. 0.446 very roughly falls in here, but we know it's definitely inside the critical region. So we say that 0.446 is greater than our critical value of 0.3438. So there is evidence that the product moment correlation coefficient is greater than 0. However, if we're in a different scenario and the product moment correlation coefficient was outside of the critical region, then we can say there isn't evidence. So look at the mark scheme. We get 1 mark here for correctly stating our hypotheses. We get another mark here for getting the critical value. And then we get a final mark here for a correct concluding statement such as this. Barbara believes that a non-linear model will be a better fit to the data. She codes the data using m equals log base 10 of x and c equals log base 10 of y, and obtains the model c equals minus 1.82 plus 0.89 m. The product moment correlation coefficient between c and m is found to be 0.882. Part B says we need to explain how this value supports Barbara's belief. essentially means to explain why this value supports that a nonlinear model will be a better fit to the data. So I'm going to say here is that the value is closer to 1. So we can see here it was found to be 0.882, but before it was only found to be 0.446. And how the product moment correlation coefficient works, the closer the value is to 1, the stronger the positive correlation is. So in this case, because it's closer to 1, we know that it's likely to have been a better fit to the data. For part B, we get 1 mark here for saying something like the value is closer to 1, or there's a stronger positive correlation, something along those lines. So lastly, we're going to look at part C. So we need to show that the relationship between y and x can be written in the form y equals a multiplied by x power of n, where a and n are constants to be found. And this is for 5 marks. So looking back up to the information earlier, we can see, okay, so we've got that c equals minus 1.82 plus 0.89 multiplied by m. And we know that she got to that by using the fact that m equals log base 10 of x and c equals log base 10 of y. So we're going to use this to sort of work backwards. So what I'm going to do is I'm going to replace c with log base 10 of y and replace m with log base 10 of x. So now we've introduced some logs, we can start using our log laws to try and get it down into a form of y equals ax to the power of m. So first I want to get y by itself as the subject, so we need to get rid of this log. So if I raise everything to be a power of 10, so I'm going to do 10 to the power of log base 10y, and then do everything as 10 to the power of, on the other side, so 1.82 plus 0.89 multiplied by log of x. I'm going to use the fact that so in this case, if we got 10 to the power of log base 10 of something, just equals that something. So essentially you can imagine this 10 and this log base 10 cancelling. This works with any base as long as these numbers are the same. So the base is the same as this number here. And look over here on the left hand side, this is the exact situation we've got. So we can essentially say, okay, so that's y equals, and then we're going to keep everything on the right hand side. So 10 to the power of 1.82 plus 0.89 multiplied by log of x. Next, I'm going to split this up using our indice laws. So we know this indice law where we add the powers here, but I'm going to use it in reverse. So I'm actually going to split this up. So I'm going to say y equals 10 to the power of minus 1.82 multiplied by 10 to the power of 0.89 multiplied by log of x. Now I'm going down to the next step. There are a couple of things we can do. So we can now evaluate this in the calculator, which gives us 0.015. Then I'm actually going to use log laws within the power up here. So I'm going to bring this 0.89 up to be the power here. Using this log law here saying that we can sort of bring the power down, or in reverse we can bring the power up. So doing that, I'm going to multiply by 10 power of log base 10 of x to the power of 0.89. Now what we've got ourselves here is in the situation we are earlier, where we've got 10 to the power of log base 10. So using the same rule here that we did earlier, we can just say, okay, so this is y equals 0.015 multiplied by x power of 0.89. Now we finish the question, we've got it in the form y equals some constant a, so a is 0.015, multiplied by x to the power of some constant n, which in this case is 0.89. So we get 1 mark up here for realising that we can replace c and m. We get another mark for getting down to this line and making y the subject. We get another mark here for both these lines. So realising we can split it up using our indice laws, and then bringing the 0.89 up to be a power. And then we get 2 marks down here for getting both 0.015 and 0.89. Magali is studying the mean total cloud cover in octas for Lucas in 1987 using data from the large dataset. The daily mean total cloud cover for all 184 days from the large dataset is summarised in the below table. One of the 184 days is selected at random, and part A says we need to find the probability that it has a daily mean total cloud cover of greater than 6. Okay, so looking up here at the table that summarises the data, if it has a cloud cover of 6 or greater, we see, okay, so it has to be 6, 7 or 8. And adding up the corresponding values here, we're going to have 52 plus 52 plus 28. So that's 132. So that's 132 days out of the total of 184 days. So if we do that, we're going to have 132 over 184. And that simplifies down to 33 divided by 46. which is our final probability. And we get the 1 mark here for getting the correct final probability, either like this as a fraction or as a decimal or percentage. So next it says that Magali is investigating whether the daily mean total cloud cover can be modelled using a binomial distribution. She uses the random variable x to denote the daily mean total cloud cover and believes that x can be modelled by this binomial distribution here. Using Magali's model, we need to firstly, in part B, find the probability that x is greater than or equal to 6. So look at this, the issue that we've got is in our calculators, they're set up to work out probabilities using the binomial distribution in this format here where we've got our random variable is less than or equal to something, rather than here where we've got our random variable is greater than or equal to something. So if we can write this in this form, then we can put it into our calculator and work out the final answer. So I'm going to write out some numbers to help demonstrate this. And we're finding the probability of x is greater than or equal to 6. So I'm going to start with 6. And I'm going to write some numbers greater than it. So we've got 6, 7, 8. And I'm going to go the other way as well. Go 5, 4. And drawing on at the minute, what we want to find is the probability that x is greater than or equal to 6. So here. Now the trick to use is that you then take this and imagine flipping it over. So if I do that, I get this region here. So flipping over our final region that we want, we get this region, which is that x is less than or equal to 5. And we need to remember that when we flip it over like this, what we need to do is 1 minus the new probability. So essentially, the probability of x is greater than or equal to 6 equals 1 minus the probability of our new region here. So x is less than or equal to 5. So going into the binomial CD menu in our calculator, we can input our upper value as 5 and look up at the distribution used. We can see we're going to input n to be 8 and p, so the probability to be 0.76. So doing that, we're going to get 1 minus, and the value that the calculator gives us, 0.296722 ... And if we evaluate this, that gives us 0.703 to 3 decimal places. So looking through, we get 1 mark here for realising that we can write the probability that x is greater than or equal to 6 as 1 minus the probability that x is less than or equal to 5. And then we get the second and final mark for working out that the final probability is 0.703. So now the second part B says we need to find to 1 decimal place the expected number of days in a sample of 184 days with a daily mean total cloud cover of 7. And this is for 2 marks. Okay, so again, we're going to be using the same model that we used in the previous part. However, looking here, we see that the random variable x denotes the daily mean total cloud cover. However, we don't want it just for 1 day, we want it for 184 days. So to work out the expected number, what we're going to do, we're going to work out the probability that x equals 7. But then, because we don't just want 1 day, we want 184 days, we're going to just multiply it by 184. So we can evaluate this in our calculator, this time using the binomial PD menu, setting x equal to 7, then using the same values for n and p as before, so 8 and 0.76. And doing that, we're going to get out from the calculator 0.2811 ... And we're going to multiply that by 184, which equals 51.7385 ... which equals 51.7 to 1 decimal place. So you get 1 mark here for realising that we need to multiply by 185. And we get a second mark here for the final answer of 51.7. So in part C, we need to explain whether or not our answers to part B support the use of Magali's model. So we can look at a couple of different things. First, if we compare part A and part BI, we can see in part A the probability of a daily mean total cloud cover of 6 or greater is 33/46, which is 0.717. And look at what we got in B part 1 when we use the model, we got 0.703. So the numbers are relatively close, so that shows that the model is likely to be quite accurate. Then we can also compare something else, so look at B part 2. We see that for over 184 days, we see the expected number of days in a sample of 184 days with a daily mean total cloud cover of 7. The model says that it should be 51.7. And if we look at the actual data from the large data set, we can see it was 52. So those are really similar, so that shows again that the model is likely to be accurate. So we see that part A and part BI are similar. And also the expected number of 7s matches the number of 7s in the data set, so Magali's model is supported. And we get 1 mark for writing a statement along the lines of this. So there were 28 days that had a daily mean total cloud cover of 8. For these 28 days, the daily mean total cloud cover for the following date is shown in the table. And part D says we need to find the proportion of these days when the daily mean total cloud cover was 6 or greater. So similar to in part A, When it's 6 or greater, it's going to be this, so 6, 7, or 8. So if we add up the corresponding numbers, we're going to get 5 plus 9 plus 9, which equals 23. And that's out of the 28 days that the table represents. So we're going to have 23 out of 28. And that equals 0.82142, ... which equals 0.821, 3 decimal places. And we're going to get 1 mark here for getting the correct proportion. So lastly now, part E says we need to comment on Megali's model in light of our answer to part D. So look at this in part D, from this set of data here. When the daily mean total cloud cover was 6 or greater, we got the proportion to be 0.821. However, this differs from what we got from this data in part A. So if we remember, 33 over 46 equals 0.717. And it also differs from here in part B, part 1, which is 0.703. So these two are quite similar. However, with this one, the difference is greater. And because in this table here, the data is for a day that follows, where the previous day had a high cloud cover, so a cloud cover of 8. It seems like there's more likely to be high cloud cover if the previous day had high cloud cover. So this sort of suggests that the days aren't independent. So the cloud cover on a previous day could affect the cloud cover on the next day. And we know for the binomial distribution, the trials, so in this case the different days need to be independent. So this would suggest that Megali's binomial model might not be suitable. So we say that part D differs from part A and part B. So look at that, the conclusion that I would then come to. Therefore, Megali's model may not be suitable. So you get 1 mark here for the first line, so for having some sort of justification and giving some evidence. And then we get a second mark for coming to the conclusion from that evidence. A machine puts liquids into bottles of perfume. The amount of liquid put into each bottle, d millilitres, follows a normal distribution with mean 25 millilitres. Given that 15% of the bottles contain less than 24.63 millilitres, part A says we need to find to 2 decimal places the value of K, such that the probability of D being between 24.63 and K equals 0.45, and this is for 5 marks. Okay, so I'm going to start off by going through and writing down what we know. So we know that the random variable D is normally distributed with mean 25 millilitres, but then we don't know the standard deviation. Also referring to this line here, we see the probability of D being less than 24.63 equals 0.15, because that's 15% as a decimal. So that's what we know so far. And before we can get on to the next bit, we need to essentially work out what sigma is here. So work out what the standard deviation is, and then we can move on to the next part. So the way we can do that is referring to this here. So here I've got the standard normal distribution, and we normally represent this with the letter Z. So you see that Z is normally distributed with a mean 0 and standard deviation of 1. So we can use this and this in conjunction to work out what sigma is here. So using the standard normal distribution, we're going to write this. So we're going to say the probability, and this time we're going to use Z, because we know Z's defined over here, and is less than. And then we're going to match this part up with this over here. And what we do, okay, so we're going to use this number here as our x here. And we already know, because we've been told in the question, that mu is going to be 25, so we can replace that. And then we don't know sigma, and that's what we're trying to work out, so we're just going to leave that as sigma. So we're going to get 24.63, take away mu, which we know is 25, all over sigma, which equals 0.15. So now what we can do is use our inverse normal mode on the calculator. In inverse normal mode, we're going to make sure tail is set to left if the calculator lets you choose that. If not, don't worry. Then I'm going to select area to be 0.15. And because here we're using the standard normal distribution, we're going to set sigma to be 1 and mu to be 0. Then we're going to click enter and see what we get. So we get minus 1.0364. So therefore, we know that 24.63 minus 25 all over sigma equals minus 1.0364. So this is great now we've got to this point, because essentially we've got an equation with one unknown, which is sigma. So we can just solve for this and work out what it is. So I'm going to multiply both sides by sigma and divide both sides by this number here. We're going to get 0.357. So therefore, we've now got enough information to write out the full distribution. So we say D is normally distributed with a mean of 25 and a standard deviation of 0.357 that we just worked out. So now we've done all this work, we can look back at what part A wants us to find. So we need to find to 2 decimal places the value of K, such that the probability of D being between 24.63 and K is 0.45. Now quickly, to help visualise something, I'm going to draw a line here. And if I label on here, so let's say this is 24.63, and here's K. This is the area that we want. But we want to think about if there's any other way to write this. So what we could do is write the probability of D being less than K, because that's going to be all of this area here. Okay, so we've covered the right area, but we've also got this little extra bit, so we need to take this away. So I'm going to take away the probability of D being less than 24.63. So hopefully that makes sense why that is equivalent to all of this. So again, this is going to be equal to 0.45. However, from earlier in the question, we found out that this, if we look up here, is actually equal to 0.15. So we can replace that with 0.15 equals 0.45. So the probability of D being less than K equals, so if we add 0.15 to both sides, we get 0.6. Then we're going to work out K using inverse normal on our calculator. However, this time using what we worked out here, so that mu equals 25 and sigma equals 0.357, and setting the area to be 0.6. And that gives us 25.09 to 2 decimal places. And this right here is the final answer. So we get our first mark here, so getting down to this part using the standard normal distribution. And then we got our second mark for rearranging that and getting the correct value for sigma. We got our third mark for this line here, so saying the probability of D being less than K is 0.6. Then we get 2 marks for the rest of our working, so getting down to K equals 25.09. So moving on to part B, a random sample of 200 bottles is taken. And part B says we need to use a normal approximation to find the probability that fewer than half of these bottles contain between 24.63 millilitres and K millilitres, and this is for 3 marks. So now firstly we're going to think of this as our binomial distribution. So we're looking at whether bottles contain between 24.63 millilitres and K millilitres. So a bottle is either going to satisfy that, so going to be between these values, or not. So there are 2 possible outcomes. So we can think of this as a binomial distribution. Right, so if we say Y, so that's distributed binomially, with M being 200, because there's a sample of 200 bottles, and P, so the probability. If we look back up at part A, we see that the probability of it being between 24.63 and K is 0.45. So we're going to have 0.45 here. Now, with regards to a binomial distribution, we know that the mean is n multiplied by p, and the variance is m multiplied by p multiplied by 1 minus p. So doing that, the mean is going to be 200 multiplied by 0.45, it's going to be 90, and the variance is going to be 90 multiplied by 1 minus p, so 49.5. So we can then use this to write a normal approximation to the binomial distribution. So we say y, which is distributed binomially here, so it is approximately distributed, we're going to call it w, with a normal distribution, and we're going to put the mean and variance in here. So that's 90 and 49.5. And look back up the question, so it's a random sample of 200 bottles, and we want to find the probability that fewer than half of these bottles contain between 24.62 millilitres and K millilitres. So fewer than half will be less than 100 because it's a sample of 200 bottles. So probability, I'm working with y, we've got y is going to be less than 100. And it's going to be approximately equal to the probability that w is less than. Now here we're going to need to use a continuity correction because we're modelling a discrete distribution with a continuous distribution. So it's going to be less than 99.5. And now we can work out this probability on our calculator. So going into our normal CD mode on our calculator, we're going to set the lower to be a really low number, so I'm going to do minus 1000. We're going to set upper to be 99.5. Then we're going to set mu to be 90. Then we've got to be careful here because we've got 49.5 here. However, this is the variance, and in the calculator we need to put the standard deviation. So we need to put the square root of 49.5, and we get 0.9115 ... which equals 0.912 to 3 decimal places. So you get 1 mark here for this line, and we get a second mark down here, so for implementing the continuity correction. Then we get the third and final mark for the correct probability of 0.912. So lastly, take a look at part C. The machine is now adjusted so that the standard deviation of the liquid put into the bottles is now 0.16 millilitres. Following the adjustments, Hannah believes that the mean amount of liquid put in each bottle is less than 25 millilitres. She takes a random sample of 20 bottles and finds the mean amount of liquid to be 24.94 millilitres. And part C says we need to test Hannah's belief at the 5% significance level and stating our hypothesis clearly. And this is for 5 marks. So first we're going to state our hypotheses. So our null hypothesis, so H0, is that mu, so the mean, equals 25. So we're referring back up to this line here, where it says that Hannah believes that the mean amount of liquid put into each bottle is less than 25. So for the null hypothesis, well, we're going to assume that it's not less than 25. We're going to assume that actually it is 25. And the alternative hypothesis is what Hannah believes here, is that H1, so that the mean is less than 25. Now we're going to get some other information that we need. So we've got a sample of 20 bottles, and the mean amount of liquid in the sample is 24.94. So we can say, okay, so we've got n equals 20, and we've got the sample mean t equal 24.94, and we see we're testing at the 5% significance level. So first thing we're going to do is we're going to assume that the null hypothesis is true. So assuming that's true, I'm going to use the random variable d, because we're talking about liquid measured in d millilitres. So d is normally distributed, and assuming that H0 is true, that's going to be 25. And looking back up in the question for the standard deviation, we can see, okay, so that's now 0.16. So it's the standard deviation 0.16. We need to remember that it's squared, which gives us the variance. So assuming that H0 is true, d is distributed normally with a mean of 25 and a standard deviation of 0.16. So now we know for a random sample of size n taken from a random variable, and here we've got x, which is normally distributed with mean of mu and standard deviation of sigma. The sample mean, so x bar, is normally distributed, again with the same mean, but with the second parameter, so the variance, being the standard deviation squared all divided by n, so the sample size. So doing that in our case, because we use the random variable d, so the sample mean is going to be normally distributed, and we're still going to have 25 as our mean. And then for the second parameter, we're going to have 0.16 squared, all divided by our n, which is 20. So now what we do is using this, we're going to say, okay, so the probability, d bar, being less than the sample mean, so 24.94, and we can work that on our calculator using these values here. So we're going to go to normal CD. We're going to set a really lower value, so I'm going to say minus 1,000. We're going to set our upper value to 24.94. We're going to set our mu be 25, and our sigma, so we need to remember to square root this. So our sigma is actually going to be 0.16 divided by the square root of 20. When we press equals, we get that to be 0.046766. ... So now we're going to compare this to the significance level. So if I round this, I'm going to say, okay, so therefore, I can say 0.047 is less than our significance level of 0.05, so 5%. Therefore, now I'm going to write a little conclusion. Since it's less than our significance level, we can say, okay, so we're going to reject the null hypothesis. There is significant evidence to support Hannah's belief. So to support the fact and say yes, it is likely that the mean amount of liquid put in each bottle is less than 25 millilitres. So we get 1 mark here for our hypotheses. We get another mark here for defining the distribution of the sample mean. We get a mark here for working out this probability. We get a mark for this part here, so saying our probability that we just worked out is less than 0.05. And we get a final mark for a concluding statement wrapping all together.